Question 4 from tutorial 6. This is our sequence. The terms are given by n factorial divided by 2 to the n. Now, in contrast to the approach used in the previous two questions, we find that it is not very useful to use the corresponding function as in questions 2 and 3. The reason for this is because if we tried to define the corresponding function, we would have to understand how we should define x factorial, seeing that in this case the corresponding function will be x factorial divided by 2 to the x. But we don't really know how to define x factorial. A remark here is that it is possible to define a function that does extend n factorial to a function on the real line. It is precisely the gamma function, given by this integral. The integral from 0 to infinity of s to the power of x minus 1 times e to the minus s. Note here that we are integrating with respect to s, and in this formula x is a constant, and this would define the gamma function. It can be checked using standard integration methods that gamma n, the value that gamma takes at the natural numbers, is indeed given by n minus 1 factorial. It is therefore true that the gamma function does extend the usual factorial function, but we won't say any more about it. I would encourage you to check the corresponding Wikipedia article about the gamma function. For this question, it turns out that we need a different method to solve the problem, and here is how we're going to do it. We observe that for the terms in the numerator and denominator, there are precisely n factors in both of these terms. Certainly we can factorize n factorial into the factors given here: n, n minus 1, n minus 2, and so on until we come to 1. There are precisely n of these numbers. In a similar way, we can also factorize 2 to the n. There will be just n copies of the number 2 in the corresponding factorization of 2 to the n. Having this before us means that we can rewrite the terms of our sequence in the following way. We will split up the individual terms into a product of n terms. So to each factor from n factorial, we will attach a copy of 2, and that would give us this identity. We start with n over 2, then n minus 1 over 2, and so on until we come to the last term, 1 over 2. Because we are taking n towards infinity for this sequence, it is enough for us to assume that n is so large, sufficiently large, such that all of these terms from n over 2 to 3 over 2 are always going to be greater than 1. You can just take n to be a really large natural number, and certainly at some point you would have picked a number n such that n is greater than 2, and therefore even dividing by 2 would still give us a number that is greater than 1. And if n is really large, then we can also guarantee that numbers all the way until 3 over 2 will be greater than 1. With this in mind, we can study the product of these numbers from n minus 1 divided by 2 to 3 over 2. Well, in this case, you see, multiplying by 2 over 2 is multiplying by 1, so it doesn't have any effect. Seeing that all of these numbers from n minus 1 over 2 to 3 over 2, they're greater than 1, and again they are also all positive numbers, it means that when we multiply all of them together, we should get a number that is also greater than 1. So this would provide us with a lower bound to the terms of our sequence. Let us see how we would do this. Alright, so here is our factorization of the terms of our sequence, and we have already obtained a lower bound for this portion from n minus 1 over 2 to 3 over 2, or even up to 2 over 2. So this bit has a lower bound, and we produce it over here. This bit is greater than 1, and therefore what would remain when we create this lower bound would be n over 2 n half. So therefore we do know that n factorial divided by 2 to the n is greater than n over 2 times 1, the lower bound for the terms in the middle, times half. And if we multiply these together, we get n over 4. So in other words, if n is sufficiently large, or even taken to be greater than 4, or at least 4, then all of these terms will be greater than n divided by 4, which is also going to be greater than 1. If n is greater or equals to 4, then this is already greater than or equals to 1, as you can clearly check. So this inequality is true for all n sufficiently large. And we see that when we take n towards infinity, it certainly is true that n divided by 4 also goes to infinity. Therefore, we know that because all the terms here, the terms of our sequence, and the lower bounds, they are all positive numbers. This would imply that as we go towards infinity, this lower bound will push the terms of the sequence that we want towards infinity as well. And consequently, we see that it means the limit as n tends to infinity of n factorial divided by 2 to the n is infinity, which is to say that the sequence diverges. There is a certain amount of intuition behind this formula, and it is that seeing that we have a ratio of n factorial and 2 to the n, what we are seeing here is that n factorial is growing so fast as n goes towards infinity, such that even if you divide by 2 to the n, an exponential function, it cannot slow down the growth of n factorial to obtain convergence. The growth of n factorial is so great that not even an exponential function can allow us to obtain convergence, to get a sequence that would converge. That is what this formula tells us, roughly speaking. This gives us the solution to question 4.